So Mat 26, section 4.6, the rank. Before we start with the rank, that would be the second half of the section. The first half of the section, we'll talk about what we call row space. Before, we talked about column space of a matrix. Do you guys remember that? So
Yes.
here we're going to learn about the row space. So if we are given a square matrix A with A, B, C, D, then A transpose, so this is A transpose. How do you find A transpose? You make rows columns and columns rows. So A, B, C, D, like that. Row becomes column, column becomes row, because we need that. Also, we recall the column space of A, COL of A, and that's the column space of A, is the span of all the columns of A. Means it's the linear combination. It contains all the linear combinations of the vector or the column vectors of A. That's what this is. So this is set of all linear combinations. Linear combinations of column vectors. Column vectors. So we introduce a definition here. The first definition, we say the set of all linear combinations of row vectors, not column vectors, is called the row space. So the row space of a matrix. If we are given an m by n matrix, then each row vector of A, so each row vector of A is a subspace of Rn. Okay, and we will show you how to use this later on. And then we use as a simple ROW of A to represent the row space of A. Or some people, they just write like this, ROW of A without parentheses. That's the row space of A. We're going to learn how to calculate or find the row space of A today, or row space of a matrix. We're going to look at this example. So what are we going to do with this matrix? These are the rows, so we write them this way: row spaces or rows for the matrix A. The book uses this notation. Some people use a different notation. Some people use this, like 302. So if you see it somewhere else with a different notation, it means the same. It means the same. So these are row vectors of matrix A. So what I'm going to do is find the transpose of A by making rows columns and columns rows. So why do we need to find A transpose here? Well, I'll show you. So if we take the column space of A transpose, what is it? It's these columns, right? Assuming this is a linearly independent set, which we probably at some point we need to prove it's linearly independent. But assume here it's linearly independent, and it should be. So that the column space of A transpose is given by this. This column space of A transpose is going to be the row space of A we're looking for. Any questions up to this point? Theorem, we say if two matrices A and B are row equivalent. Row equivalent means one of them, if we make changes on one of them to obtain the other one using elementary row operations, then we call them row equivalent by performing row operations. So if you take matrix A, do some row operations and get a new matrix, that new matrix is matrix B. These two matrices are called row equivalent. If that's the case, then the row space of A and the row space of its equivalent matrix B, they should be the same. And we'll see how this theorem helps us to find the row space of a matrix. Okay, so let's say they give us matrix A and matrix B. Okay. So A and B are given. B, they will tell you B is a row equivalent to A. So B was found by taking matrix A and do row operations and get B. What is B written in which form? In which form is this?
Row echelon form.
Row echelon or reduced echelon form, right? Because what you see. So we have here two non-zero rows, as you can see. So if B is in echelon form, the non-zero rows of B form a basis for the row space of A and the row space of B. Okay, row space of A, they form a basis. Now the question is how to find row space of A given A and B are equivalent. So this sign means equivalent. It's like a tilde sign. So here the row space of A equals row space of B. And what's the row space of B? So you can use parentheses as the book does, 103, comma, 010, right? That's coming from B. So that's the row space of A. Again, the main thing is we need to find the row space of A. We took its equivalent matrix B and we found the row space of B, which is the one that contains the non-zero rows. This is, it's a basis. It's a basis for the row space of A and row space of B. See, we took out the rows with the zeros in B. So given, let's look at another example. Matrix A. 1, -1, 5. -4, 2, -6. 9, -4, 10. -7, 1, 7. Okay, this is equivalent to matrix B that I'm gonna give you. 1, 0, 0. 0, -2, 0. -1, 5, 0. 5, -6, 0. And this is equivalent to matrix C that I'm gonna give you. Oh my god. 1, 0, 0. 0, 1, 0. -1. -5 halves, 0. 5, 3, 0. So what do we have here? I give you, this is the original matrix. I give you the one in the echelon form. And then I give you the one in reduced row echelon form of that matrix. And we're gonna ask you to find a lot of things. Let's say find, let me see, find the bases Find the basis for the row space of A. Find the basis for the row space of A. The column and the null space of A. Okay, we're gonna find the basis for all of these. Some people give you just A and you have to see on your own. So to find the basis, first we find the basis for the row space of A. Remember, the basis for the row space of A is the same as the basis for the row space of B, which is basically the rows, the non-zero rows of B. That's the first one.
Sorry, are these columns?
So now the basis for the column space of A. What does it require us to do? To find the column space of A, what does it require us? So they want us to, here we need to find which columns are pivot columns, right? Which is this, right? So what we do here to find the basis for the column space of A is what? Is make sure, don't write that one in the RREF. You take the original one. It's the first column in the original, and the second one in the original. So those are called the pivot columns. So how do you find the null space of A? This is usually found by setting AX equals 0. Remember? So if I look at the reduced echelon form, it was given as 1 0 0 0 1 0 -1 -5 halves 0 5 3 0. So this, from here I can get x1 minus x3 plus 5x4 equals 0, and then 0x1 plus x2 minus 5 half x3 plus 3x4 equals 0, right? So from here, so here x3 and x4 are free variables. So x1 equals x3 plus minus 5x4, and x2 is 5 halves x3 minus 3x4. We need the parametric form of that, so you can probably say x1, x2, x3, x4 equals x1 is x3 minus 5x4, x2 is 5 halves x3 minus 3x4, and this is x3 and x4. So you get x3, 5 halves, x3, x3, and 0 plus -5x4 minus 3x4, 0 and 1. Then you can take x3 out, you get 1 5 halves, 1 0, plus take x4 out, -5, -3, 0, 1. So then the basis for the column space of A is gonna be these two vectors, 5 halves 1 0, comma -5, -3, 0, 1. This is something that we learned before. Sorry, this is the null space. That's what I think what someone else meant. That's That's a null space, not column space. So to practice more on this, so I'm gonna ask you find the bases for row space of A, column space of A, and null space of A. If, let's say, A is given as -2, 1, 3, 1, -5, 3, 11, 7, 8, -5, -19, -13, 0, 1, 7, 5, -17, 5, 1, -3. And this is equivalent to B equals 1, 0, 0, 0, 3, 1, 0, 0, -5, -2, 0, 0, 1, 2, -4, 0, 5, -7, 20, 0. And this equivalent to C 1, 0, 0, 0, 0, 1, 0, 0, 1, -2, 0, 0, 0, 0, 1, 0, 1, 3, -5, 0. So for this one, so the basis for the row space of A would be the first one 1, 3, -5, 1, 5, comma 0, 1, -2, 2, -7, and 0, 0, 0, -4, 20. The basis for the column space of A. So you see, you look here, here, these are the pivots. So it's gonna be in the original, the first -2, 1, 3, 1, the next one -5, 3, 11, 7, and the last, and then 0, 1, 7, 5.
I have a question about
So the next one is to find the basis for the null space. So we look at the last one. We have x1 plus x3 plus x5 equals 0, and we have x2 minus 2x3 plus 3x5 equals 0, and then x4 plus minus 5x5 equals 0. So from here we have x1 equals -x2 x3 minus x5, and x2 is 2x3 minus 3x5, and we don't know what x3 is, so it's like it's like a free variable, and then x4 is 5x5, so x3 and x5 are free variables. And I'm sure everyone knows how to get the parametric form of this one. So in this case we get x3, let's see, -1, 2, 1, 0, 0, plus x5, -1, -3, 0, 5, 0. Okay, so then the basis for the null space of A is given by -1, 2, 1, 0, 0, -1, -3, 0, 5, 0. Is it 0 or 1 here? 1, 1. That's a 1. So that talks about or that covers the first half of this section. So now we continue with this section, talk about the rank and the rank theorem. So what is rank? Definition. What is a rank? the rank of matrix of A. It's the dimension of the column space of A. And if you remember that, that's the number of pivot columns in A. So again, the dimension of the column space of A. So what we do is we take, let's say we have a matrix like this in echelon form. Then what do we do? We have a pivot here, pivot, and a pivot. Actually, wait, let me make this 0. So rank of A is 3. That's the number of pivot columns in A. Also, good to know that the rank of A transpose is the dimension of the column space of A transpose, which is the dimension of the row space of A. Let's say A and B are two matrices that are row equivalent, and the dimension of the row space of B is 8. Find the rank of A transpose. So because they are row equivalent, then automatically means the dimension of the row space of A is also 8. So now the rank of A transpose is the dimension of the row space of A, right? Which is 8. That's what the note says right before this example. So what we have, note, so note, we can call or name the dimension of the null space of A. The null space of A equal the nullity of A. Just in case if you see this, that's what it means. Some people call it nullity of A. So then from here we introduce the rank theorem. The rank theorem said for an m by n matrix, we have the rank of A plus the dimension of the null space of A is n. Okay, is n. That's what the rank theorem. Or some people can write rank of A plus the nullity of A is n. Either one is fine. Recall, rank of A is the number of pivot columns of A. This, the dimension here, or the nullity of A, is the number of non-pivot columns of A. In other words, number of free variables for which AX equals 0, and n is the number of columns, because it's m by n, and m rows and columns. If the null space of A, matrix A, or let's call it of a 7 by 6 matrix, is 5-dimensional, what is the rank of A? So quick, this is m by n, so this is means m is this, n is 6. When they say 5-dimensional, the null space dimensional, this is the dimension of the null space of A. Okay, the null space of A. So by the rank theorem, the rank plus the dimension of the nullity or the null space of A is n. So the rank of A, we're looking for that. This one is given 5 and n is 6. So the rank of A is 1. Another example, if A is 6 by 4 matrix, what is the smallest possible dimension of the null space of A? So if it's m by n matrix, this is m by n, so n is 4 here. What is the smallest possible dimension? So we need to find the dimension of the null space of A, the minimum. Okay, the minimum. So I don't know what the matrix is, so what I'm gonna do is 6 rows, 4 columns. So assume it's like this. So what is the null space? Null space of A is the number of non-pivot columns, right, of A. How many pivot columns, if possible, we can have? Well, just think about it this way. This could be a pivot, right? This could be a pivot, this could be a pivot, this could be a pivot. So this tells us the maximum you can have as pivots is 4, right? 4. So we can have 4 pivot columns if possible. It might not, but that's the max we can have if. So in this case, since there are 4 columns, then the smallest possible dimension of the null space of A is 0. Just keep those in mind. First one, that the rank of A is the number of pivots. So it's also the number of linearly independent. The next one, or let me just put them as 1. That's the same as the number of linearly independent rows, and that's the same as the dimension of the column space of A, and the same as the dimension of the row space of A. How about if they give us a matrix A and they want us from scratch to find the rank for this? So to find the rank of A, we can do so by either finding the number of pivots, or we can find the number of base vectors in the column space of A, or we can find the number of base vectors in the row space of A. To use the number of pivots, we go with row operations, row reduced for A, which I found it already, and I'm assuming everyone can do that. 3 0 0, 2 -7 thirds 0, -4 14 thirds 0. So how many pivots? 1, 2. So rank number of pivots. Note, the row space of A is 2 dimensions, the 2 bases vectors in the row space. There's 2 non-zero vectors. Another example. A is given like so. We need to compute rank of A. 2. Compute the nullity. 3. Verify the rank theorem, or some people call it rank nullity theorem. So to do that, we start with RR, row reduction, and I got 1 0 0, negative 2 0 0, 0 1 0, negative 2 negative 2 0. What's the rank of A? How many pivots? 2 pivots. So that's the dimension of the column space of A, which is 2 pivot columns. Note, if you remember what we did today, if you go back to the original matrix, negative 1, negative 2, 0, the first column, and the third column, 3 1, negative 1, this is the basis for the column space of A. Part 2, we need the nullity. We need to find total number of non-pivot columns. Number of non-pivot columns. So how many is there? How many non-pivot? Well, we have this one and this one, the second and third columns. There are 2 of them. Number 3, how do we verify? A was 3 rows by 4 columns, so n is 4, right? N is 4. So the left hand side, it says the rank of A plus the nullity of A. Rank of A is 2, we found it. Nullity is 2, so that's 4. And the right hand side is basically n, which is 4, so that verifies it. Any questions about this? Last thing I want to add here is a theorem, the invertible matrix theorem, which we introduced before, but what we're going to do here, we're going to add to it. So say continued, we're going to add to it. So say you have m by n matrix, the statements listed below are equivalent to the statements that A is an invertible matrix. So we stop before n, before m, so now m, the columns of A form a basis of Rn. N, the column of A is Rn. The dimension of the column space of A is n. The rank of A is n. The nullity, the null space of A is the 0.